Good morning, everyone. My name is Yunsup Lee, and I finally get to talk to you about Zscale, which is our tiny 32-bit RISC-V systems. And during the presentation, I'll also give you some updates on the RocketShip Generator. And I'd like to acknowledge all Alberts in our lab who made all this happen. So what is Zscale? It is a tiny 32-bit RISC-V core generator suited for microcontrollers and embedded systems. And over the past months, we've been talking to you guys, and unanimously, you guys told me that I want to use the smallest RISC-V cores. So we actually listened to your feedback, and we built one. So, and on top of that, we made Zscale to design. We designed Zscale to talk AHB light buses rather than our proprietary buses. So what that means. So does everyone know what an AHB light bus is? So it's AMBA 3, it's what the Cortex M series use. So that means it's plug compatible with the ARM Cortex M series. So you can take it out, put Zscale in, recompile, the memory map doesn't change, and it should be good to go. So the generator also generates the interconnect between the core and the devices. That includes the buses, slave muxes, and crossbars. So what are all these RISC-V core generators from Berkeley, which are following the trade name, right? So Zscale is generating a family of tiny cores, which are similar in spirit to the ARM's Cortex M0, M0 Plus, M3, and M4. It integrates with the AHB Lite interconnect. The Rocket generator generates a family of in-order cores. Currently, it only supports the 64-bit single issue processor only. We have plans to work on the dual issue 30 and have the 32-bit options as well, so that it can execute the RV32G ISA. It's similar in spirit to the ARM's Cortex A5, A7, and A53. And it currently talks a proprietary memory interface, but we are actively working on to change it to an AXI4 interconnect. So, and there's finally Boom, which generates a family of out-of-order cores. It supports 64-bit single issue, dual issue, and quad issue. It's similar in spirit to ARM's Cortex A9, A15, and A57. And we have also plans to integrate it with the AXI4 interconnect. Chris will talk a lot more about it at the talk right after this one. He will kind of give you how the performance spectrum looks like for all these cores. So the Zscale pipeline is a very simple 32-bit three-stage single-issue in-order pipeline. There is half a stage here, PC Gen, which gets fused into other stages. So you start counting from, so it has the fetch stage, it has the decode and execute stage kind of fused into one stage, and there's a write back stage. So all the normal integer operations go through this three-stage pipe, and there's a bypass path from the write back to the decode. It executes the RV32IM ISA, which has 32 registers, and all the performance counters are mandatory. And it supports the M and U privilege modes. And the iBus and the dBus here coming out, the request comes out of the PC Gen stage, the response comes back in the fetch stage, the dBus request goes out in the execute stage, the response comes back in the write back stage. All these buses are AHB Lite and 32 bits wide. So if there's a memory instruction stuck in over here, or the multiply instruction or the divide instruction is going on here, all the instructions are stuck in the decode stage and cannot proceed further. Interrupts are also supported because we're supporting the M and U privilege modes. And this time we will actually publish a microarchitecture specification of this to standardize this simple three-stage pipeline so that there's only one kind of implementation out there. So how does Zscale compare to Cortex M0? So M0, the ISA, is actually ARM v6. The Zscale is the RV32IM. Both are single-issue in-order three-stage pipes, and in terms of the DMIPS per megahertz for performance, we are slightly better. And if you map both of them to the 40-nanometer technology library, we're slightly bigger, but there's a reason for that. It's because ARM's v6 only has 16 registers, and RISC-V has 32 registers. And in this area calculation, there's actually a unrolled multiplier and divider, as well as all the 64-bit counters that were mandatory to execute the RV32I ISA. So in terms of the area efficiency, we divide these numbers, we're a little bit better. The frequency, we don't put any arbitrary restrictions on how fast you can synthesize and place and route it. So it goes about up to 850 megahertz on a 40 nanometer technology. So that's good. And the power, it turned out to be a little bit lower. But note these numbers are very likely to change as we do performance tuning and things like that on the core. So we've noticed that when it's a very small design, one register actually counts. So that's why we kind of try to standardize this RV32E base ISA. It's a new integer-based ISA. It's a reduced version of the RV32I designed for embedded systems. We cut the number of integer registers to 16 and remove all the counters that were mandatory in RV32I. So that means you don't need to implement the read cycle and the read cycle H, read time and read time H, read instruction, retire H are not mandatory anymore. So the Zscale currently doesn't have an option to deal with this, but we will add this option to turn on the RV32E base ISA. So how does Zscale fit into the entire system? So this is how you build a system. So you start from a core here, and those were the iBus and the dBus. You put them into a crossbar, and you put all the memories that you want to keep close to the processor, which the devices don't need to touch. So you put like your NOR flash, boot ROM, SRAM over here. And then you also connect to the system bus, the S bus here, and you hang all the DRAM, the devices, which kind of need the burst, the burst support. And for the peripherals, which don't need the burst support, you just put it on an AHP to APB bus over here and put all the peripherals, hang them off this P bus over there. And this time, we actually implemented a JTAG debugger. It also talks an AHP Lite interface over here, so it plugs into the AHP Lite crossbar as a master, so it can insert all arbitrary loads and stores to your memory map, and there will be connections between the JTAG debugger and the Zscale core so that you can stop the core or put breakpoints and interrogate the internal state, things like that. You notice that this is now, you can build a self-hosted system out of it, so we're actually going to be working on the platform spec to standardize the system as well. Fortunately, and for some people, unfortunately, Zscale Generator is written in Chisel. Do everyone know what Chisel is? Okay, here's a 30-second version of it. Chisel is a new hardware description language embedded in Scala, a modern programming language, and it's been developed at UC Berkeley. It's open sourced. Chisel is not HLS. We're just trying to productively try to put down registers and muxes using a modern programming language. So we rely on good software engineering practices such as abstraction, reuse, object-oriented programming, functional programming, and tongue-in-cheek, we build hardware like building software. So I wrote 604 unique lines of code in Chisel. The control unit is 274 lines. The data path is 267 lines. Out of that, 99 lines could actually have been generalized in the Rocket source code base to deal with 32-bit and 64-bit things. I plan to do so you can kind of discount that number in the future. The top level is 63 lines, which glues those two things together. And actually, this time we borrowed 983 lines from Rocket. We did not write those lines. Those lines were already verified. So reuse and parameterization in Chisel and RocketShip actually does work. Okay, maybe this is not good enough. So I'm going to do something novel. Everyone advised against this, but I'm going to show you some real code on crossbars, and I'm going to show you how you productively write that with functional programming. But before that, I tried this yesterday at the poster session, and I realized if I don't do functional programming 101, there's absolutely no chance that I'm going to let you guys know what's going on. So here's a list. I have 3 elements, 1, 2, and 3, and you map it with a function. So the function takes an argument and returns n+1. So what is the result? 2, 3, 4. Great, that's simple. So now, this is some Scala syntactic sugar there. So why are you repeating yourself like n over there? So you just say underscore. That means I want that element over there. So it's going to kind of do the same thing. So now we're going to zip things together, two lists with 3 elements, 1, 2, and 3, and A, B, and C. So what's the result? So zip means I'm going to take the first element of each list, make a tuple, and then make another tuple with the second elements and another tuple with the third elements and return a list. This is really helpful when you're trying to connect two things together. You zip them, and then you connect them. So how do you extract the first element out of this tuple? Well, you do ._1. It's because the tuple doesn't have names for the fields. So if you have a struct-like type things, you can actually name the subfield over there, and that will give you the content of that field. And that returns 1. OK, so now let's look at some even crazier things over here. I told you everything now. Now this makes sense, right? What's the answer? Oh, by the way, it's the same as this, right? It's actually 1, 2, and 3. So yeah, so this means I want that guy and the first element of that tuple, right? Great. Oh, and so these are maps, those are zips, but what if I don't care about the result? I just do a for each, right? So in this case, I do 0 until 3, will return 0, 1, and 2 as a list, and for each, I will print it out. So it will print out on the console 0 and 1 and 2. Great. So with this, I'm going to try to convince you that Chisel is pretty cool. This is actual code that I wrote. It's the AHB Lite crossbar. OK, so this is a crossbar that I plug into iBus into DBus and all the devices down there, right? So there's 2 AHB Lite masters and 3 slaves over there, OK? So here are the 2 primitives that I'm going to give you. The first one is this bus, where there's this master and there's 3 slave ports. And depending on the address, it will route that request to the right slave according to the address map, OK? So now, but what if there are 2 guys actually want to talk to the same slave? Well, you need to put the slave mux, which is an arbiter. I don't know why they call it a slave mux. So there are 2 slave ports coming in, and it arbitrates, and it gives the result out, right? So with these 2 primitives, how do you build a crossbar? This is the answer. You put 2 buses down, connecting the masters, and you put 3 slave ports in front of all the slave muxes in front of all the slave ports, and you connect the first port of each masters to the first slave mux, the second output to the second slave mux, the third to the third slave mux, OK? So this is literally the 10-liner for this, OK? So now let me walk you through. Don't panic. So this is actually defining a module called AHB crossbar. And there's 2 arguments to it. The first one is the number of masters. And the second one is an address map, which is also a Lambda function, which takes an address and evaluates whether that address is supposed to be routed to that guy. Great. So this is the I/O definition of this crossbar. You can see there's a list of, this is a list of masters, which is the AHB master I/O. And there is a list of slaves, which is, so this is pretty neat, amap.size. You get the number of guys hanging off here. And then the AHB slave I/O. So that's the I/O definition of the module. And here's the instantiation of this bus, right? You map over the number of the I/O.masters, and you instantiate the AHB buses, and you return the I/O port of that module. Okay? Now, I also instantiate a bunch of muxes. I do a map over the I/O.slaves, and then I instantiate the slave muxes, and I return the I/O. Okay? I hope I didn't lose anyone so far. Okay, so the first line here is I'm connecting the ports from the AHB crossbars to the input ports to the AHB Lite buses, right? So I do buses.map, and I want to get the master port of all buses, and I zip it with the IO.masters for that class, and for each, I just connect them. That's a Chisel connection, which connects 2 IOs. Great. And then now I'm going to do this connection over here. I do a for loop over all the number of masters and the number of slaves, and I connect so I'm connecting all these 3 ports first. So I'm connecting this guy to that guy, this guy to that guy, this guy to that guy. And then the next iteration, it will connect the other guys. And finally, it's pretty simple now. You zip the list of slaves and the output of these slave muxes and connect them together. It's pretty neat, isn't it? So once you thanks a lot. So functional programming, the neat thing about this is once you have formulated it this way, it's correct. It's correct by construction hardware building. Like, good luck writing this in Verilog. So, if you're still not convinced, good luck. The 4th output, you just add another, address map to this list, and you're good. You don't need to change anything inside here. If you want another master port, just when you're instantiating, put 3 there. It's if I can't sell you Chisel with this slide, well, good luck. But okay, you know, I learned this lesson. I'm not going to fight that battle. So this time I'm going to do things differently. So we actually writing the Verilog version of the Zscale core. A human is writing it, not Chisel. So that's also going to be released. You know, we talked to a lot of people, and we also heard your feedback and concerns. So we're going to write that in Verilog. So it's currently 1,215 lines of code. And that means there are no more excuses for adoption. I gave you the smallest core in Verilog, which is AHP Lite compliant. I don't know, yeah. So, but please do let us know if you have any more concerns. I will kind of try to get it fixed. All right, so this was the demo system that I showed you yesterday. Some people probably have seen it. This is an instantiation of the template that I showed you before. So there's actual devices here. So the boot RAM is a BRAM mapped onto the Xilinx FPGA. So the way that it gets initialized is with the initial bit file. I just programmed the program in so that when it boots up, there's instructions sitting over here. On the S bus, there are the DRAM, SPI flash over here, and then on the AHP APB bus, there's the simple GPI LED and the core reset register, which is tied into this core register over there, so that the JTAG can program the reset of the core. And this is kind of the memory map that I came up with. So the Zscale core boots up, starting executing instructions over here, and then you can do load and store to the DRAM, the SPI flash, the GPIO LED, and the core reset. So I mapped this to a Xilinx Spartan LX9 board, which is an AVNet board, which you can buy it at $89. It has a lot of things. Xilinx initially built this board, I think, to show off the microblaze. So it has the SRAM, the flash, the Ethernet, ART, JTAG, PMOD headers, LEDs, and it is pretty good. So today, after the talk, I'm going to raffle these 4 boards. So I hope you are holding to that little thing that Tammy gave you when you registered. So this is the resource utilization. The LUT count is a little bit higher, but we're going to try to map all the things on the board, and we're going to optimize it. So the test program that I showed you yesterday, it's actually stored in the boot RAM. What it does is, as soon as it wakes up, it initializes an LFSR register, and it writes to all the 64 megabytes of the DRAM, and then it initializes the LFSR again to the same seed, and it starts reading the 64 megabytes again. And as you go, it starts toggling the LEDs by writing to the memory map. So the Zscale use cases, you can use it as a microcontrollers to implement your simple control loops. If your code density matters, I think Zscale would be a good use case. And even for embedded systems, you can actually build your system around the little template that I showed you. Like we have all the buses and things like that. But if you already have a Verilog implementation, which is already verified, then you can still use that because the Zscale processor is plug compliant to the HP Lite buses. And for those, the observers who are, just don't want to use our code, well, you can treat it as a validation of tiny 32-bit RISC-V systems. You don't need to use our code, but I think it's a good existence proof of the RB32i can actually be built with a very small system. So both of the Chisel and the Verilog versions of the Zscale is open sourced over here. And the FPGA, kind of the shim that we built around, is also open source over there. Currently, you can't actually build it out, check it out and build it right now. There's some code cleaning that I need to do, and I need to integrate it into RocketShip Generator. So we will soon post a blog post on how to check everything out and build it. It's going to be very soon. So I'm going to switch gears a little bit. Does everyone know what the RocketShip Generator is? So really briefly, it's a parameterized SOC generator written in Chisel. It can generate an arbitrary number of tiles with rocket cores, floating point units, L1 caches, and it can also generate the uncore, which is a banked L2 cache, and each bank is a coherence master point, so all the memory accesses coming out of the tiles are kept coherent, things like that. So we have a bunch of updates. We've been actually actively been working on this. So since the first RISC-V workshop, we have implemented the L2 caches, the banked L2 caches with directory bits to accelerate cache coherence. Now the Rock accelerator actually has a port into the L2 caches over there. And we internally had a private repository called reference chip, and we've been cherry picking commits to share with the RocketShip. And we've ran with the model for a couple months, and I think we utterly failed. So we're going to scrape that, and we're going to move all our development to the RocketShip branch, which is going to be open source. So you guys will be able to see all our progressions and all our bugs. And please don't complain if it doesn't work. And we had all these proprietary memory interfaces called MEMIO and things like that, but we're going to start moving over to more standardized interfaces. So, however, we're going to still keep our Tilelink interface, which is our cache coherent interface, because I think it's strictly better than whatever's out there. So if you want to learn more about it, I gave a talk on the RocketShip Generator last workshop, so you can go watch my talk. And so today I use AXI4, AHB, and APB bus names, but I just did that to minimize confusion. Going forward, we're not going to call them that. We have our own names, starting with NASTY. It stands for not a standard interface, and that's our implementation of the AXI4 interface. There's going to be HASTY, which stands for Highly Advanced System Transfer Interface. Thanks, Don. It's our implementation of the HB Lite standard. And there's finally POKI, which is Peripheral-Oriented Connection Interface, which is our implementation of the APB bus. And our code base has already started using all these names. So this is going to be like a quiz next time. I'm gonna ask you which bus is what. All right, great. So this is the RocketShip Generator grand plan, how it fits in with the Zscale processor right here, right? So there was originally this HTIF, which was our host DMA engine, which we used for tethered systems and things like that. But we're going to try to standardize everything. So we're going to move to a JTAG debug interface over here. So here's our Rocket Tiles L2 banks, and you can plug in your cache current devices either to the L1 network or to the L2 network. And the L2 network, there's going to be these Tilelink AXI4 bridges and an AXI4 crossbar where you can connect all your DRAM controllers and high-speed IOs over here. And this is kind of going to be your Zscale complex over here, where it's going to be connected between this AXI4 and AHB bridge. And on this bus, there's going to be the Zscale processor and all the low-speed I/O, scratchpad, and the system control registers. And you also can connect peripherals over there. And this time, the CSR files are all going to be memory mapped over here. So that means that the Zscale processor can serve as your system maintenance processor to, inject all the loads and stores to read these random registers, the control status registers, and react to it. For example, if you want to do DVFS on the cores, the Zscale will be able to program all that. Okay. So that, and also, one thing that we're working on is we're going to try to have uncached loads and stores coming out of the Rocket Tile and be supported throughout the cache coherent region, just skipping all of it, and be injected into this so that the Rocket Tile could also do memory mapped I/O to the entire memory system. So that's our grand plan, and this is how Zscale will fit. All right, in conclusion, Zscale is a RISC-V tiny core generator suited for microcontrollers and embedded systems. So for Zscale, future work is the microarchitecture document will be released first. We're going to work on improving performance, and we're going to implement the C extension as an option. We'll also add the MMU option to boot Linux, and we're going to support more devices on the LX9 board, and that's forthcoming. So on the RocketShip Generator, we're going to dump HTIF, and we're going to start implementing the JTAG debug interface, and we're going to move to standardized interfaces, NASTY, HASTY, POKI, and add the Zscale option. All right, raffle time. All right, I think I have 2 minutes for questions.
Don Stark from Google. How do you know that your HB Lite implementation is correct? What have you verified it against?
Right, so that's where I need some help. I cracked open the HB Lite spec, and I did as much as I could in terms of the understanding the bus spec, but at least just for some validation. So the DRAM interface that I actually use Xilinx's IP, which was, it exposed an AXI4 interface. So I put their IP, HB Lite to AXI4 interface. So I was talking to that. But I suspect my crossbars and my buses and my slave muxes have bugs in it. But so I'm going to try to, write a stress tester going forward, and I'm going to try to test it. I only had like a week to write all the buses and mux and crossbars, so it's really buggy. But at least I think the processor complex part of it is somewhat correct. So.
Does it support byte and half-word accesses?
I'm sorry?
Does it support byte and half-word accesses?
Yes, it does. Yes.
So is there a plan to standardize the ROC interface? Because there are cores coming out outside of Berkeley with their own coprocessor interfaces.
Do you have any standards to suggest?
No, I'm saying if ROC can be a standard, or
ROC
is there
is
a plan?
already kind of standardized. We've been using it to teach classes and such, so students have been reading some document to understand
But
what's
it's not part of the specification, so.
right. It's not.
So
But
what are your thoughts on?
I think there should be a separate specification that's written and released on the Rock Accelerator.
Rishi Nikhil from BlueSpec. So I really like your example with maps and zips, close to my heart, because we've been doing that with BlueSpec as well. As we know, we are derived from Haskell, and we use similar functional programming techniques. But I do think it's oversell to use the term correct by construction. It isn't. You can still write wrong programs in Chisel or in BSV or any language you give me, right? You haven't formally verified that you've put together the things correctly, right? So you can, it is oversell to call it correct by construction.
Okay. Almost correct by construction. Well, at least I'm confident that it's going to do the right thing.
Just
Yes.
apropos the slide yesterday, that was a short speech disguised as a...
Yes, I was kind of thinking about that.
Yeah, two questions. One is,
All right.
what type of multiplier and divider does Zscale have?
So right now, it was an iterative divider and multiplier, which was unrolled 6 times. And that's also a parameter that you can change. So my understanding is in some implementations, you want a combinational multiplier.
Yeah.
We can support that too.